Hello. In this video, we're going to continue our discussion of Chapter 6, looking at thermochemistry by taking another look at the first law of thermodynamics, talking about work. I've said we're not going to focus a lot on it, but I do want to have just at least a brief discussion of work and specifically pressure volume work, and then what units we use to talk about energy. Right? Thermochemistry is all about transfers of energy, so we need to describe the units. We went over this in class a little bit, but I do also just want to make sure it's covered in the videos as well, so you can have that when you're reviewing this. So just a quick reminder of what the first law of thermodynamics is. It is that the change in energy for an isolated system is equal to 0. Or another way of saying this is that delta E for something that's not isolated, and by definition, an isolated system, we said the energy can't be exchanged with the surroundings. So it means you can't create energy out of nothing. We can also say delta E if we sort of divide the whole universe into the system, as we discussed previously, and the surroundings around it. If we add those together make up the whole universe, right? Because the surroundings is everything but the system. So we could say that any change in energy for our the total of the system plus surroundings, right, would be equal to delta E for our system plus delta E for the surroundings will equal to 0. Again, this is just another way of stating the law of the conservation of energy, that energy cannot be created or destroyed. Another way we can think about the first law, though, is that any change in energy for our system, or for the surroundings for that matter, will be equal to Q plus W. Q, again, just as a reminder, let's define these again. We've defined these previously, but Q being heat, or any energy is exchanged due to temperature changes. And that's our thermal energy that we're talking about, right? Our molecules moving around and having that kinetic energy, whereas work is from pushing things around, is sort of how I like to think of it. So we're mostly, like I have previously mentioned, we're mostly going to be focusing on heat exchange, but I do want to briefly talk about work and how we can think about work in terms of chemical reactions. So work we can define as pushing against a pressure. So we'll think about this as what we call PV work, or pressure volume work. So this is work done by gases. So this would be work done by, like, filling up a balloon, for example. When you blow up a balloon, the volume increases because you're increasing the pressure inside. So that's pushing against the pressure of the gas on the outside. So that's some work that happens. You can also think about work in a engine is usually done with pressure volume work, where you have some gas that heats up because of burning fossil fuels, and that expands a piston that pushes on a crankshaft, and then that's what actually provides the work that moves your car around. So this type of work we can define with an equation where work is done by changing a volume and pushing against a pressure, and we define it to be negative P times delta V, where delta V is our change in volume. So we're going to see this symbol a lot, this delta symbol. Just as a reminder, this means change. So just want to reiterate that. So we see it over here, delta. This is a Greek letter, the Greek letter delta, which is essentially like D. I don't know why that's the one we use to mean change, but it is the one we use to mean change, so it shows up a lot, and we'll see that quite a bit. Okay, so pressure volume work, we can write out this way, that it's going to be negative of the pressure times the change in volume, and so that gives us a way to calculate work. There are additional types of processes we can consider, but this is sort of the most basic way we can think about this. Now, if we're looking at this, you may look at the units here. Hopefully you think about that. Pressure we usually write in terms of atmospheres, so if we're thinking about this equation here. And volumes are in liters, so a change in volume would still be in liters. And you might look at that and say, is that units of energy? And it is. 1 liter atmosphere is equal to 101.32, I want to make sure I have this right, joules. But what's a joule? So let's talk a little bit about energy units. So the most common energy unit we're going to use is joules. This is the SI unit of energy. And it's not terribly relevant for this class, but if you ever take a physics class or upper level chemistry classes, a joule is composed of other SI units. It's a kilogram times a meter squared over second squared. So we can make it up out of these other SI units of length and mass and time. So largely this won't matter for this class, but in case it's so that you've at least know that, or aware of the fact that this is true. And this is where this comes from. So a joule is the energy it takes to accelerate a 1 kilogram object 1 meter per second in the distance of 1 meter, right? So it can tell you about forces, right? Forces exerted over a distance, right? Because that's energy or work. Another really common energy unit that we're going to see is the calorie. You're probably familiar with like counting calories or calories in food. And this is related to that unit, but is not exactly the same. So a little c calorie is the amount of energy needed to heat 1 gram of water 1 degree Celsius. So if you have 1 gram of water or 1 milliliter, since the density is about 1 gram per milliliter, and you want to heat it up by 1 degree, it takes 1 calorie of energy. And there's a relationship between calories and joules. So 1 calorie is equal to 4.184 joules. So these are related to each other. And the other thing that is useful to know units-wise is that 1,000 calories, which is of course 1 kilocalorie, is what we call 1 capital C calorie, and this is the food calorie. So when you look at the calorie content of your food, it is the unit of energy, right? It's how much energy is present in that food that you're going to eat and take into your body. And so that calorie is actually 1,000 of these little c calories that are 4.184 joules. Primarily in chemistry, you'll see calories, you'll see kilocalories, and you'll see joules. Another one that shows up, of course, is kilojoules. Will show up quite a bit, which is, of course, 1,000 joules. So just to reiterate some of those prefixes that we've seen, these are common units that you're going to see. Now, this is just energy for a total amount, and oftentimes we're thinking about an energy per mass or per mole. And so often there we'll see things like kilojoules per mole or kilocalories, sometimes per gram even. And so those are other units that we're going to see pop up. So we've been introduced to the first law, a little bit more about work, that we can figure out work with this equation, thinking about pressure and changes in volume. We'll do maybe some simple questions related to that, especially in your homework. But mostly we're going to focus on heat because that's the primary energy change we're going to look at. And so in the next video, we're going to move into talking about another function that we use to keep track of energy in the types of systems that we care about in chemistry.